Let's consider the SU2 Higgs mechanism. We saw last time that, before last time we saw that if we simply had a theory of scalar bosons with a certain symmetry, we typically had some massless bosons and some massive scalar bosons, massless scalar bosons and some massive ones. And these massless ones were called Goldstone bosons. Then last time we considered gauging that the symmetry of the action of the scalar fields. And when we did that, we saw that some or all of the gauge bosons required a mass through the Higgs mechanism. And the case we examined was the ON Higgs mechanism. Now we're looking at the SU2 Higgs mechanism, and then we'll go to the actual Higgs mechanism, which is SU2 cross U1. The action density is minus dA phi dagger dA phi. I'm following my notes, which I put on the web page, and so this is section 7. And then this is 1 over 4K trace FAB. This is the Yang-Mills field strength. FAB is a commutator of d mu with d nu. Well, obviously, if it's FAB, then it's the commutator of dA and dB, not d mu with d nu. And then there's the term m squared, y squared, and just to follow my notes without changing things, it looks like this. Phi is a complex doublet, phi 1, phi 2, and the gauge fields are anti-Hermitian, i.e. sigma over 2 dotted into A, B. So this B, maybe I should have used mu. This B is a space-time index, and the 3 sigmas of SU2 are dotted into the 3 A's of the gauge boson. The sigmas, of course, are the Pauli matrices. I could write them down, but I think you have seen them before. They're not as, we don't invoke them as frequently as we invoke the harmonic oscillator, but they're in second place. Okay, so what is dB of phi I? So B is space-time, I is 1 or 2. And that is, of course, dB of phi I plus AB ij phi j. And so that is dB phi I plus IE sigma over 2 dot A AB, and there's B left out there, ij phi j. And even more explicitly, this is dB phi I plus IE over 2 sigma k ij ak b phi j. Okay, so with all the indices explicit, that's what this is. And this is invariant under the SU2 transformations. Phi prime of x equals u of x, phi of x, where this is e minus I theta of x dot sigma over 2 phi of x. So this is a 2 by 2 matrix, and this is a 2-component complex vector. And A prime, again, B of x is u of x, a b of x, adjoint of x, plus, I'm a little puzzled that we've got the dB acting on the u like this. It may be that that's because of this minus sign up here. Anyway, so I'm not certain about this term, but it may be okay. Okay, and of course we have the trace relation, a half sigma I, a half sigma j equals a half delta ij. It's the sigma I, sigma j. If I and j are the same, it just gives 1. And the trace of 1 as a 2 by 2 matrix is 2. 2 divided by 4 is 2. That's that 2. So effectively, for this theory, this k that occurred there is a half. And since this theory has gauge symmetry, we can rotate to a unitary gauge. Let me turn the lights on in the hall. I really find that. People think because they go home at 5 that everybody else should go home at 5, or that everybody else has gone home, or if they haven't gone home, they don't deserve any lights. Okay, anyway, so we go to unitary gauge. I hope the Blonda looks at these notes. I'm trying to see her massive influence on my behavior here. Okay, in unitary gauge, this phi of x is going to be this. It's going to be 0, v, plus some s of x, where v is some constant that will minimize the Higgs potential, and s will be the radial vibrations of about v. And we'll say the vacuum value in this Higgs, in this unitary gauge is just 0 v, v being a constant. And we can figure out what v is. In this particular theory, it would be 0 is partial v partial phi squared. And that would be m squared minus lambda over 2 phi squared. And so v squared, lambda v squared over 2 would equal m squared. And so v is m over square root of lambda square root of 2. All right. Okay. All right, so now we focus upon this term and see what happens to the gauge bosons. And what we'll see is that we get mass terms for those gauge bosons, and the mass terms, of course, come from the gauge fields, come from this thing here. In other words, you've got, this is the covariant derivative. And so it's the ordinary derivative plus this thing. But phi assumes the value 0v in the vacuum. And when it is 0v, the square, or the absolute value squared of the covariant derivatives gives us a term, and I'm just going to keep the part having to do with phi. It is the following form: i.e. sigma k ij over 2 akb phi j dagger from the left term, and on the right, i.e. sigma m over 2 il am b, well, upper b in this case, phi l. So that's the mass term for the gauge bosons. And in simpler matrix notation, this is equal to e squared over 4, I times minus I being 1, e squared over 4, phi 0 dagger, sigma k, sigma m, phi 0, a k b, a m b. And I see I left a 0 out of here. Okay, now remember sigma k, sigma m is delta km times the 2 by 2 identity plus I epsilon k m l sigma l. That's the Pauli matrix relation. And consequently, if we look here, this thing here in K and M is symmetric. So we can symmetrize this. So this mass term then is E squared over 8 phi 0 dagger, the anti-commutator of sigma k with sigma m. In other words, this is symmetrizing, but it brings in a factor of 2 that I cancel here. Phi 0 akb amb. And, well, of course, this thing symmetrized is just, it's actually 2, isn't it? Right, this is then 2 times the identity, so this is e squared over 4 phi 0 dagger, just the 2 by 2 identity. And then phi 0 akb amb. And so that is e squared over 4 v squared abk amb. I have an 8 here, so I'm just 8. I guess there's a factor of 2 off in my notes. In any event, this thing is m squared over 2 akb amb, and so the mass squared is then e squared b squared over 2, or the mass is EV over root 2. And you see that all the gauge bosons get the same mass. So I'll have to chase down that factor of 2 later tonight. So they all get the same mass, and no mass is unbroken because the symmetry is completely broken. The group H, by the way, that leaves the vacuum invariant, well, it's just the identity element, because all the SU2 generators move the move 0V. Sigma 1 and sigma 2 obviously change this, but even sigma 3, e to the minus I theta sigma 3 acting on this turns this into V e to the minus I theta over 2. Depending on where you put the 2. We can think about this one more time. Just briefly, imagine that we put phi not as a complex doublet with 4 real fields, but in a real triplet, 3 real fields. Well, then what would we have had? We would have had the ON model for n equals 3. And in that ON model, it's as I said, what we just studied. And to go back to the ON just for a second, what we found then was that that in that case we only have 2 gold-stone bosons because we have 3 generators of SU2, and if you imagine the 3 possible directions that the Higgs field can point in, if it points up, then rotations about the z-axis leave it invariant. So we have then 2 bosons get a mass, but not the third one, not the third gauge boson. Okay, but in this case, we've got all the gauge bosons getting a mass. All right, now I'm going to skip sections 8 and 9 because we treated them in following Schwartz. Now I want to go to the Electroweak model, which is something that's been experimentally verified and moreover, which is more or less understandable, whereas QCD has some intrinsic residual mysteries in it that are pretty confusing. Okay, so for the Higgs mechanism, I'm going to change notation a little bit. I'm going to replace phi by capital H. The symmetry is U of x, H of x. H is a doublet, so it's basically H1, H2, like that. Each H is complex. So it's the Higgs structure is the same as over there. But the gauge structure is different. Now we have A mu prime is U of x, A mu of x, mu adjunct of x plus d mu U of x, mu adjunct of x. And U of x now is e to the ig sigma a alpha a. The alphas are parameters depending on x, and then IG prime, the 2 by 2 identity matrix, beta of X. So it's basically an SU2 and a U1. So we call this SU2 cross U1. And what's truly weird about the standard model is that the SU2 acts only on the left-handed fermions, as you know. But it's weird. And moreover, the U1 is simply a U1, and it has bizarre quantum numbers. So obviously there's something wrong with the standard model, and what's amazing is that it works so well. In fact, the embarrassing thing is that despite all the experiments that have been done, there's been no departure from the standard model detected at all, at least not, more than maybe a 3 sigma anomaly at the LHC. I don't know how many sigma it is exactly. In fact, I've forgotten what it is. Does anybody remember? In 2 years, it may go away. With luck, by the way, apparently they've turned the machine on, but it's just running at low energy. They're trying to get it going at higher energies. And real collisions at 13, let alone 14 TeV, apparently won't happen until June. And, well, if there's something totally startling, like it starts producing sausage or something, then probably unexpected, then we'll know in June. But if instead the run at high energy is as close to the standard model as the run at low energy, it'll be months, if not years, before we see anything new, if then. Anyway. Okay, so this is the transformation. Let me repeat the action, and I'm changing it slightly by a factor of 2 over there, which may have to do with the factor of 2 that I saw there. Anyway, this is going to be minus d mu h dagger d mu h plus, let's just say a half rather than screw around with k, f mu nu m squared h squared minus lambda h squared if you want. And of course, h squared is h1 dagger h1 plus h2 dagger h2. That's what we're talking about when we say h squared. So the minimum of the potential, well, let's see, I should say what d mu h is. D mu h then is I d mu plus ig sigma a summed from 1 to 3 over 2 mu plus ig prime I over 2 again b mu h. And all right. I guess the reason we put the 1/2 here is so that the trace of this squared is a half. Okay, so what's the minimum of the Higgs potential? It's 0. It's at partial h squared, and this is equal to 2 lambda h squared minus m squared, and so in the ground state, the absolute value of H has to be, has to vibrate around this ratio, which we call V over root 2. Or equivalently, we'll say that H0 is the mean value of the Higgs field in the ground state, and I should have said we'll go to unitary gauge. This is in general, because this is gauge invariant statement. We're going to unitary gauge, and in unitary gauge, this is 1 over root 2, 0V. The reason for the 1 over root 2 is that we want V to be the field normalized correctly. And in unitary gauge potential, imagining now that this V can vibrate in the real direction only about V, then this thing is I see there's a typo here, and now I have to imagine what I was saying. So let's just look at the Higgs. Yes. It's the Higgs field is m squared h squared. So h squared is a half v squared times m squared. And then there's this term, which is minus lambda, but now it's root 2 to the 4th. So that's actually 4. And v to the 4th. So that's what we're talking about. Now we compute the second derivative there. So let me just circle this typo. Taking the second derivative, we get 3 lambda v squared minus m squared. And what is this second derivative? Well, this second derivative is the mass squared of the Higgs. The Higgs being the thing that vibrates in the real direction about V. And why do we know that this is this? Well, remember in the very beginning of these notes on masses, I said that for a real scalar field, this is the mass term, so if that's V, so mu squared is equal to V double prime. So it's the mass squared is V double prime, and in that case it's this. But now what's lambda? Well, we know what lambda is. Lambda over here, you see, is m over v. And so if we stick lambda in here, let's see, let me get this straight here in my notes. Let's instead stick in v. V is m over lambda. So v squared here, we have 3 lambda. V squared then is m squared over, wait a second, I think I got a square root. Yeah, there's a square root. It goes like that. Okay, in other words, h is m over square root of 2 lambda. And so v squared is m squared over lambda minus m squared, and that's 2m squared. And 2m squared is, let's see, what should I say? Well, 2m squared is mh squared. And so mh is then square root of 2 times m, which is square root of 2 times v times lambda. Okay, now, we'll be analyzing the gauge structure of how the gauge fields interact with fermions in maybe 10 or 15 minutes, or 5 or 10 minutes. And experiments at LEP and at other places showed that showed what V was. We learned that V was 246 GeV. On the other hand, experiments at the LHC in 2012 showed that MH was about 126 GeV. And so the self-coupling lambda now I see here, I have it here as M over V squared. Oh, this is wrong, isn't it? It's the square root of lambda is M over V. So lambda is M squared over V squared. All right, unfortunately I didn't compute that. I'm sorry, so more typos. All right, let's do it on the fly. Well, this is about a half, so this is about a quarter.
Good enough.
All right, so I have the square roots all correct. This is about a quarter. So the self-coupling is less than 1, which is a good thing. Otherwise, we'd have another mystery on our hands. Any questions?
Just some simple ones.
Yeah, well, those are the best kind, because then I can answer them.
The G and the G prime are the coupling constants for the weak and the electromagnetic.
Right. G and G prime will be playing roles in the electroweak interactions of the fermions, as well as everything else.
Okay. And then why do we change the sign on the second derivative? This all counts as 1.
No.
Well, on your V0 or V.
Wait, let me get a better chalk. These chalks, they make good marks, but after a while they get kind of dull.
So right there, why did we change the sign when you took the second derivative?
Where the hell did I take the second derivative?
Right in front of you. There you go. And then one equation up is the original.
Oh, well, I mean, yes, good point.
L minus V.
L is always kinetic minus potential.
Okay.
So the potential is lambda h to the 4th minus m squared h squared.
Okay.
All right, well, so I must say, it's really nice to be able to write down this number and to write these equations. I hope I didn't screw up the factors of 2. But because the last 20 or 30 years, or 40 years, we've thought there's a Higgs, probably. Don't know its mass, but it didn't take very long to find out what V was. Experimentally. Well, because we knew what the we knew something about the electroweak interaction, so we just had to match what we knew to this theory, and then we get an idea of what V is. And but in basically every lecture that everybody gave until 2012, the summer of 2012, they had to say, well, this is still a free parameter because we don't know what the ratio of M to V is. All right. Okay, so now let's let's stay in unitary gauge. And of course, after spontaneous symmetry breaking. And so what are the mass terms for the gauge bosons? All right. Well, of course, they come from this term, where you replace h just by 0v over root 2. So pulling out the root 2's, what we have is minus a half 0v, and now this is g sigma a over 2 aa mu plus g prime I over 2 d mu. So this is the gauge field for the U1, and we call it U1 of hypercharge, and this is these are the gauge fields for SU2 left. Doesn't know it's left in this expression. All right. So this is what we have to multiply out.
What happened to the ID mu? So in the d mu h over here before. you have
What
an ID mu
happened to
term?
the
So what? 2 terms to the left. The identity times dv. Yeah. Why do we not have that? In this?
why don't we have the derivative?
Yeah.
Great question. It's because we're just ignoring the derivative terms. The derivative only acts on the fields that are vibrating around the minimum, and we're ignoring them.
Yeah. So it's not going to give us a term that we're going to call a mass term.
Right, they don't give us a mass term, and they're small compared to V. V is huge, 246 GeV, and the vibrations are apparently, you know, they're so small you can't even hear them. All right, but you certainly are entitled to a candy. Okay, so this is what we've done, and now we know what the Pauli matrices are, and so this thing is, we pull out these factors of 2, we get minus 1/8, 0v, and then this whole structure is a 2 by 2 matrix. G A3 mu plus G prime B mu, G A1 mu minus I A2 mu, G A1 mu plus I A2 mu minus G A3 mu plus G prime B mu. Okay, so that's the mass term, rewriting it as a matrix. So 2 vector, 2 by 2 matrix, 2 vector. Freshman algebra. Okay. All right, so now, what are we doing? What we're doing is we're looking for the 2-2 matrix element. Oh, wait a minute. I've done something really stupid. Hold on. I should follow my notes, of course. My left arm was probably down when I wrote that. There's another matrix here. This one. Yeah. What's that?
Yeah, I was wondering, I thought maybe you multiply.
All right, I'll give you 2 candies in just a minute. A3 mu plus G prime B mu, G A1 mu plus I A2 mu, G A mu 1 minus I A2 mu, minus G A3 mu plus G prime B mu. All right, let me get you your candies and me a drink of water. Okay,
Two chairs.
okay, so now we have a product of two 2x2 matrices, but what we're looking for is just the 2-2 matrix element. And we know that the 2-2 matrix element of this product is given by what I think of as the dot product of the second column here with the second row there. And so this is equal to minus v squared over 8 times this inner product, and let me write it as, I'll first write this row. A1 mu plus I A2 mu minus G A3 mu plus G prime B mu. And now this column here is G A1 mu minus I A mu 2 minus G A mu 3 plus G prime B mu. Okay. So it's the dot product of these two vectors. And now you see this is very simple because it's just G squared times the absolute value of this complex field. And then plus this field squared. And so that tells you immediately that there are only 3 gauge bosons that have mass. Namely, what we have here is minus v squared over 8 g squared A1 mu A1 mu A2 mu A2 mu plus minus G A3 mu plus G prime B mu, and then the square, the same thing, but just with the index raised. Okay, so what does this tell us? This tells us that there are 2 gauge fields, A1 and A2 get the same mass. And that mass within factor of 2 raised to some magic power is Vg. Then there's another linear combination of H3 and B mu. This linear combination gets a mass, and that mass is, apart from factors of 2, it's V times some funny combination of G and G prime. Okay. All right. So the first thing we do is we normalize these complex fields, and in fact we call them W plus or minus mu, and it's 1 over root 2 A1 mu minus or plus I A2 mu. Now the minus coming, being associated with the W plus is a little confusing, but apparently that's the convention. The other one normalized to z mu. And this is 1 over the square root of g squared plus g prime squared g a 3 mu minus g prime b mu. And here we're just, multiplying by minus 1. Now let's appreciate the normalization. The normalization here is that the coefficient of this guy squared plus the coefficient of that guy squared in absolute value terms is 1. That's 1/2 plus 1/2. Over here, it's g squared plus g prime squared, or g squared over g squared plus g prime squared plus g prime squared over g squared plus g prime squared. That's also 1. So the normalization is correct. And in terms of these correctly normalized gauge fields then, this Lm that we were talking about is minus g squared v squared over 4 w minus w plus mu mu minus g squared plus g prime squared v squared over 8 z mu. And so that means that mw is just simply gv over 2. And that's because when you have complex fields, you have the mass squared. When you have real fields, you have mass squared over 2 in the mass. So the mass then is gv over 2, and experimentally these were observed certainly at LEP, or LEP2, and the mass was measured to be, let us say, 80.4 GeV. And that came rather quickly, but it was sometime later that that the Z mass was determined, and in fact mz, or that the Z was found, let us say. It's g squared plus g prime squared v over 2, and that's 91.2 GeV. Okay, so these are the experimental masses, and this is the way they come about. And so, knowing these masses, one can figure out from the two masses, one can figure out, and let's see, we've got V. You see, we learned not only this, but we also can figure out what the rate is for beta decay or these other interactions of the W's with the fermion, with the charged fermions. And that allows us, that gives us three inputs: Fermi's constant, the weak that is to say, the weak interaction constant that Fermi introduced in his non-renormalizable theory of beta decay. That was measured, and then we compare this theory at low energy, and then we had three inputs years ago: mz, mw, the Fermi constant. That allows us to determine g, g prime, and v. Actually, we have another input, namely that this has to give us also the electromagnetic interactions, and we've known what the strength of those are for 150 years, if not longer. Okay, so anyway, everything was determined, but what wasn't known was V was known, but lambda and M weren't known until a couple of summers ago. We learned that the mass of the Higgs was 126 GeV. So this linear combination has a mass, a very high mass, 90 JeV. But there's an orthogonal combination of generators, and it has mass 0, and that's the photon. And the photon then is a mu, and that's 1 over square root of g squared plus g prime squared. And it looks very much like this, but there's a plus sign, and g prime are interchanged. So it's g prime a3 mu plus g b mu. So this is the photon and its massless. Now, what's really nice, I think, about this part of the Standard Model is that these masses come about from the symmetry, and they come about because the Higgs, the kinetic action of the Higgs field, in other words, this term over here, this thing has to be gauge invariant. And yet the Higgs assumes a certain value in the vacuum, and so it's that value, V, together with these gauge fields that come in d mu h dagger d mu h, that necessarily then give us the masses. So the masses are coming out with values that are fixed by the coupling constants, g and g prime, by the value v, and by the nature of the symmetry. This is in complete distinction to the other masses of the Standard Model, where we have not a zillion, we have maybe 20 different masses for the up quark, the down quark, the electron neutrino, the charm quark, the strange quark, the muon neutrino, the top quark, the bottom quark, the tau, and the tau lepton. So I haven't, what is that? That's 4 times 3, that's 12 numbers. And you just go up into the nose. You just pick a coupling, well, I'll get to what it is. It's just the interaction between the Higgs field and the fermions. And, so it doesn't have any of the, symmetry or any of the, it's just not as nice at all as this. It's worth inverting all these formulas. So we can say, for example, A1 mu is 1 over root 2, well, it's W plus mu plus W minus mu. A2 mu is 1 over I root 2, W minus mu minus W plus mu. A3 mu is 1 over square root of G squared plus G prime squared, G prime A mu plus G Z mu, and B mu is 1 over square root of G squared plus G prime squared, G A mu minus G prime Z mu. All right, so if I haven't screwed up, these are the inverse relationships that take us from the fields with definite mass to the fields with definite flavor, so to speak. So, in other words, the mass eigenstates and the flavor eigenstates for the gauge bosons are different. And in fact, the same thing is true in spades for the fermions, because there are more fermions. Okay, now let's get to the fermions. So what's the covariant derivative of a fermion that happens to have hypercharge Y? Well, d mu is I d mu plus Ig sigma A over 2 A mu plus I G prime Y 2 by 2 identity d mu. Okay. I think I'll skip one line of the text and get us to the next expression. Namely, it's I d mu plus I g over root 2. So in other words, all I'm doing is going from the flavor eigenstate, or the flavor eigenfields, to the mass eigenfields. And that's W plus mu T plus W minus mu, I left a mu out.
Also, on your, did you miss an I on your first equation?
I
On the B term? Or is that just applied? Y, you have YI,
here?
yeah, you don't have the I, well, the copy I have doesn't have the I. I guess you do.
Oh, you mean down there? Well, all right. I don't. Show me later.
Okay.
Or you want to show me now? Show me now. Yeah, that's in. Yeah, but I updated.
Okay, there you go.
So. So g squared plus g prime squared z mu g squared t3 minus g prime squared y 2 by 2 I plus I g prime over square root of g squared plus g prime squared a mu T3 plus Y. Okay, so that's the covariant derivative that acts on a doublet of left-handed fermions. T plus or minus is 1 over 2 sigma 1 plus or minus I sigma 2, so it's what you'd expect. Okay, now, as you know, one of the great mysteries in most physics books is E. On some page, somewhere, the author says we're going to take E to be positive or negative, and then never says it again, and you can find E on almost every page, and you don't know what the hell it is. I chose E positive. I suppose that's because Weinberg did. I don't know. I don't remember now. Anyway, it's g prime over the square root of g squared plus g prime squared. And why is that? Well, that's because the gauge field, the photon, this is the photon, is coupled to that. So this is the strength of that charge. On the other hand, this thing here is a matrix, and we're going to call that the charge matrix. And it's T3 plus whatever the Y quantum number is times the identity. And I've said we're acting on the doublets. If the doublets are leptons, then we typically call them EL, nu E, E. And by the way, there is something slightly schizophrenic about this whole business. When we talk about quarks, we usually are, and gauge bosons, and we talk about everything except neutrinos. by up or down or top or bottom or strange, we mean the mass eigenstate. Neutrinos, because we didn't learn about the masses until relatively recently, well, recently meaning 20 or 30 years ago, it depends on when people started believing the guy who was actually doing the chlorine experiments and choking to death in that mine underground. So historically, we just refer to the neutrinos, the electron neutrino, as flavor neutrinos. So now when we say electron neutrino, muon neutrino, tau neutrino, we mean the flavor states. That should change at some point. I don't know when we're going to have an intellectual phase transition, but we really ought to get over it fairly soon. Because since we don't really know all the relationships or even the masses of the neutrinos, or whether they're Dirac or Majorana, we still are using this obsolete, inconsistent nomenclature, which almost makes us look like astronomers. All right. Okay, so that's the lepton doublet. Of course, we have two others, namely nu mu, nu tau, tau. And for each of these, what we say is we assign this quantum number y to be -1/2. So the left-handed doublets of the leptons, we give them y equals -1/2. And when we do, then what does this thing do when it acts on the doublet? Well, it's g prime over the square root of g squared plus g prime squared, a mu t3 plus yi on EL is then E, that's this thing, a mu t3 plus IY or YI EL. And so this is E a mu Q EL, and this is, well, let me write it out. It's E a mu 0, 0, 0 minus 1, because what we've got is y is -1/2, and then we have T3, and T3 has a -1/2 here. Up here it has a +1/2, which is canceled by the y. And the thing is diagonal. And this thing is nu E. And so now I've got this -E a mu E. So this is the electromagnetic interaction. Now, unfortunately, this is a number, and this one is a field. Okay. But I've painted myself into a corner here. All right. Now, let's look at Z and A. They're related, Z and A are related to A3 and B in this way, and these things are real numbers whose squares are 1. In fact, that's just correct normalization. And so these things are therefore angles. And we can rewrite this as cosine theta W minus sine theta W, sine theta W, cosine theta W, A3 B. And of course, if you want, you can put a space-time index on this. All right, so the gauge fields are related this way. Theta W then is what? Well, it's the cosine. This is theta W is called the weak mixing angle, especially at Boston University, where Glashow is. At the University of Texas, I imagine they often call this the Weinberg angle. And on the other hand, the tradition in physics has been that authors on papers are typically listed alphabetically, so Weinberg was always in the tail of the distribution whenever he was one of several, although he typically was a single author. But anyway, sine theta weak is then g prime over the square root of g squared plus g prime squared. By the way, the Weinberg was actually at MIT when he did this work, and Glashow, I think it was Caltech or Berkeley when he did this. Anyway, they both showed up at Harvard, and after they won the Nobel Prizes, they didn't think the Harvard salary was high enough for their justly high status in the physics community, and so they moved on to wealthier positions at Boston University and the University of Texas at Austin. All right, so let's see, we have a little time left, so I should go on. Remember, Q is T3 plus yi or iy, and of course, it's hard to remember what y and I are. It's easy to remember what the charge of the particle is and what the T3 quantum number is, because it's obviously plus a half or minus a half. And so what we do is we swap yi for q minus T3. In other words, we write yi is q minus T3. And so then we have the z mu over square root of g squared plus g prime squared times g squared T3 minus g prime squared y. Now let's see, where did that show up? I'm not quite sure why I'm doing that, because I'm not sure what equation I have in mind here. Notice the coupling here. The z coupling has a g squared T3 minus a g prime squared yi. Okay. This is then 1 over same square root of g squared plus g prime squared z mu, and then it's g squared plus g prime squared T3 minus g prime squared q. Okay. So this is a slightly clumsier way of writing it, but at least we don't have to figure out, we don't have to keep reminding ourselves what the hell y is. And of course, as I've already said, I've already done the next line, namely that, well, that this one turns into just E A mu Q on whatever the doublet is. The coupling to G, we can rewrite this thing using the definition of the weak mixing angle. We can rewrite this as G over cosine theta W Z mu T3 minus sine squared weak mixing angle Q. So that's a nicer way of writing the Z mu term in the
in the coupling. All right. Anyway, E, it turns out, is G sine theta W. That, I guess, is, you can see that from here. GG prime is what we call E. So G sine theta W is GG prime over the square root. And so that means that G sine theta W is E. All right. And all right, we've already done the coupling to the photon. So finally, the covariant derivative looks like this. D mu is 2 by 2 identity, I d mu, plus I g over root 2, W plus mu T plus W minus mu T minus. So that's why there was this choice, because people wanted to do that. Plus I G over cosine theta W Z mu times T3 minus sine squared theta W Q. And then finally the term that we've known about for a very long time, i.e. A mu Q. Okay, so there are several terms. The derivative, the W charged W terms, the Z term, and then the photon term. All right. And one more relation just to finish this particular sequence here. MW is cosine theta weak MZ, and this weak mixing angle, theta W, is 0.233, roughly, at least it was when I was writing up these terms. All right, so we'll pick up here next time, which is today's Thursday, so it's next week. Oh. So we're done, right?